Good morning, everyone, and welcome to this Carbon Forum. I'm happy to have you all here. Good Friday morning and happy Earth Day as well. Welcome to Ames virtually on this rainy day, and we've got a great lineup for you and an exciting morning. So I am just going to go over briefly the schedule for this morning. We'll do a quick welcome address and have a keynote speaker at 9:20 on innovations in soil carbon measurements. And then at 9:45, we'll have an innovations panel. And then at 10, we'll take a break, or 10:20. Then at 10:30, we'll have the second presentation on implementation of soil carbon measurements, and followed up by another panel at 11, and then a closing address at 11:40. And it's my pleasure to introduce our welcome address. It's none other than our Dean Dan, the Endowed Dean's Chair of the College of Agriculture and Life Sciences at Iowa State University. He also serves as the director of the Iowa Agriculture and Home Economics Experiment Station. And Dean Dan is actually the originator of an idea that Lisa and I really like. At least last year, I think, I'm going to paraphrase it, Dean Dan, that soils are Iowa's agricultural infrastructure, and that we should be talking about soils as an infrastructure as much as we do roads and bridges, and probably caring about them as much as those too.
Great. Thank you, Marshall. Hello, everybody. Nice to see you here. We just hit 100 participants, so that's kind of an auspicious number of some kind. I want to thank Lisa Schulte-Moore and Marshall McDaniel for putting this together. I want to recognize the Iowa Farm Bureau and the Renewable Energy Group for sponsoring this. We've got two great keynote speakers, Christine Morgan and Skye Wills, and they'll have much more to say than certainly I do at the top of this conversation today. There's lots of things to recognize as well. April 22nd is Earth Day. Senator Gaylord Nelson from Wisconsin years ago took the mantle from what had been a broader conversation around the world and brought Earth Day to us here in the US. I was in 4th grade or 5th grade at the time. I remember it very well, the very first Earth Day. I created a poster that my parents were very proud of that hung on the wall of the school. And that was one of my beginnings that led me to have the opportunity to sit here today and talk to you. So Earth Day is important to all of us in lots of different kinds of ways. And certainly, Mother Earth is indeed our mother. I'll make a couple of comments about our purposes today before I turn it back to the facilitators to actually get into the intellectual part of the conversation. I want to start by saying that this is about things that are important. And we know as scientists that things that are important need to be measured, and they need to be measured well. And today's topic, today's sort of overarching question is, how do we understand and measure soil carbon and all the related factors so that we can effectively manage it? If we're not measuring things well, then obviously our management will be flawed. And so this is a powerful question, a vexing question in many, many ways, because if it was easy to do, it would already be done. And so I congratulate you and I encourage all of you forward in figuring out how to do this well so that when we expend our energy and our resources, when we try and work with policymakers and citizens and landowners and companies and NGOs and folks all across our landscape here in Iowa and around the world, that we're doing it with the right information, the right data, and that's going to require careful and appropriate measurement. And so kudos to all of you for really diving into this very difficult subject. We have long known that organic matter in soil is extraordinarily important, in many ways the basis of fertility. But now we've got to measure it and figure it out. And it's in the context, in the crucible, if you will, of climate change that we're working so hard in this arena. So thank you for doing that. The conversation about climate change, greenhouse gases, which are more than just carbon, of course, and more than just carbon as related to the agricultural enterprise, is in many ways about sustainability. And sustainability is a term that I think is great. I think it tells us exactly what it's supposed to tell us. It is often criticized, though. People will say, well, what does it mean? It means one thing to this group, a different thing to that group. How do you measure it? There are lots of people who are prone to forgetting the social part of sustainability. They think about economics and environment, but what about social? It's a complicated topic. Yesterday and last evening here on this campus at Iowa State, we had what we call our Ignite days, like igniting a fire of inspiration. And yesterday's Ignite program, which is all about student participation, student presentations, was about a Feed the World challenge. Students did remarkable work, presented all kinds of cool ideas that none of us older folks would have ever thought of. And so congratulations to the students. If you ever are down on the mouth about hope for the future, just go talk to students and you will be rejuvenated. There were several keynoters last night, 3 of them, in fact. These are people that are well into their careers. One is a person named Colin Hurd, who is a graduate of our college, an entrepreneur, works with autonomous vehicles and things in agriculture. And he talked about what it means to be an entrepreneur, and he touched on sustainability. Another was Allison Van Enneman, animal scientist from UC Davis, who talked about ways and means of doing genetic improvement, particularly in livestock, but generally in agriculture, where there's misinformation or disinformation and where the opportunities lie. And the third, not that those 2 weren't interesting, but for me, the third most interestingly was a woman named, I got it here, Ashoke Abulu. Ashoke is a 2005 architecture graduate of Iowa State University, and she's done remarkable work, including she was the chief architect for the MetLife Insurance Company and did designs for human workers in 1,500 buildings around the world. And she spoke about many, many things about the relationship between people and their work and people and their environments. And I took the opportunity to ask her what she thought about the concept of sustainability, which is in many ways your topic today. Although you're driving down on one aspect, how we measure and manage carbon, it is about sustainability. And she offered, she's a remarkable person. She offered two comments that I scribbled down as quotes. And the first one is that, quote, sustainability is about intention. It's about what we intend to do. And I think that's a really powerful way to think about sustainability. It's not just about measuring what we have done or should do or would do. It's about what we want to do. And so your conversation today is about that as well. The other thing she said, among other parts of her answer that I wrote down, was, quote, an opportunity we all have is to show up and be part of sustainability. And so she didn't define it as it's only for individuals or it's only for groups of people or nations, but that each of us have a role in it. And that would be true for all now 119 of us on this call who think about carbon, climate change, the challenges that face us across our landscapes, how people interact with our landscapes, that it's our intention to always do better and to pursue as an opportunity this thing we broadly call sustainability. So those are some broad ideas, some broad contexts that I hope you'll think about as you contemplate your work today. Marshall referred to some of my comments the last time I had the privileged opportunity to address this group or a portion of this group. And I talked about soil as infrastructure. I fundamentally believe that. I also talked about our need to actually do what in the world of other kinds of infrastructure we call deferred maintenance. So if we've got a building or a house and we haven't painted it and the paint is chipping, that's deferred maintenance. And we know we should have done it before the paint started to chip. And we have that challenge now with our soils in many, many ways. We have deferred maintenance we need to do. We have degraded our soils in virtually every part of the world. And it's on us to provide the information and the opportunities so that others with good intentions can improve the quality of our soils. And this is a huge task. We often talk about in Iowa how our farmers are some of the most, if not the most efficient in the world, that our farmers and our agricultural sector are resilient. And we talk about how our soils are resilient. All those things are true. We benefit from resilient soils because we started out with modern agriculture here in this part of the Corn Belt with soils that would forgive misuse and degradation. Our soils remain incredibly productive. Last year was one of the most productive years on record, even with weather, which wasn't always so cooperative. And that's because our systems are resilient, and most importantly, our soils are resilient. But the soils can't act on resiliency. We're just mining their resiliency. It's only people, managers, scientists, people who care about our soils who can act on resiliency. And frankly, we have deferred maintenance to do to repair and rebuild this soil infrastructure. And that's what you're all here to talk about today. So I'm going to close with that comment that we've got deferred maintenance to do. We've got resilience that our soils provide us is our responsibility. It should be our intention to preserve and to rebuild even more resilience in our soil systems. And carbon is certainly a driving force in that. Lisa Schulte-Moore and her team did the Iowa Carbon Science Task Force report that came out in February of this year at the request of the governor. A remarkable effort. We gave them a team award here in the college. And I just want to recognize that as well, that this is a group of people here and elsewhere that she and Robert Brown and others have been working with through the Bioeconomy Institute, the Department of Agronomy, the Department of Natural Resource Ecology and Management, to really be actors and players and at the forefront of these questions about carbon and soils and a more sustainable future. So with that, thank you for having me, for sharing this time with me, and have a great meeting and be intentional about your work. Thanks, everybody.
Thank you, Dean Dan. That was great. It's my pleasure to introduce our first speaker, and her name is Dr. Christine Morgan. She did her Bachelor's of Science degree in Plant and Environmental Sciences from Texas A&M University. She did a master's and PhD in soil science from the University of Wisconsin-Madison. Currently, she's the Chief Scientific Officer at the Soil Health Institute, where she establishes research priorities to advance soil health and develop the scientific strategy and implementation of soil health research programs. She's also an adjunct professor at Texas A&M, and where her research emphasis is in soil hydrology, pedometrics, global soil security. She's also an editor-in-chief at Geoderma, a global soil science journal, and a founding editor-in-chief of Soil Security. And she's on the board of directors for the Soil Science Society of America and is a fellow of the SSSA as well. At this time, I'd like to introduce Christine Morgan for our first speaker.
All right. All right, good morning, Marshall, and thank you for inviting me to speak today. Let's see here, get up my slides. Well, first I have to say that I was quite inspired by the introduction by Dean Dan. Thank you, Dean. Dan, that was really wonderful. And this morning we got an email from our CEO to encourage everyone just to stop and go outside and think about our jobs and where we are and how we can contribute to Earth Day and sustainability. And I heard that same message from you, that sustainability is about intention and what you choose to do and showing up and being part of it. So I think that's just hugely inspirational. So thank you for sharing those words. And I'm going to talk a little bit about measuring soil carbon. Primarily, I'm going to talk about measuring it in situ. And so a few times I've been asked to talk about this, and I promise that you're not going to see something that you've already seen before from me, but I always try to do something new. But I do want to start the conversation and, what does it mean when we're thinking about measuring soil carbon in situ? So I have a couple of introductory kind of get us all together on the same plane of thinking. Marshall introduced me as the Chief Scientific Officer at the Soil Health Institute. We are a small nonprofit with a mission to safeguard and enhance the vitality and productivity of soil through scientific research and advancement. And I have to say, while I loved my 15 years at Texas A&M University, it was a great experience being faculty and an academic. I love, love, love my job at the Soil Health Institute, and it's because of these faces that you see here. We have a great team of soil scientists, agronomists, ag economists, trainers, and miraculously, all of these faces are all across the United States. So I am based here in North Carolina, but this team is distributed, even not Cam, who I realize I don't have on this, is actually even in Canada. So we are we are continental in our team. We were Zoom before Zoom was cool. And anyway, I always like to just acknowledge the team because I'm speaking for the Institute, and these are the brains and minds and creativity at the Institute. So when we're thinking about measuring soil carbon in situ and at scale, there's just a couple of things that I like to just step back and think about. And this is kind of where my brain sits. You know, kind of what do we know, and where can we advance our understanding of measuring carbon in situ? And I think that, you know, the motivation behind all of this, right, is because we have carbon markets, we have some deferred maintenance on our soils. And if you treasure something, such as treasure our soils as a resource, our agricultural infrastructure, as well as infrastructure for many other things, we need to be able to measure it. And we need to be able to measure it, I think, you know, broadly and accurately as possible, but without, you know, the cost being too high, especially when it comes to soil carbon markets. I strongly believe that ultimately we have to measure the outcome. We can't just model it. And if we're going to measure that outcome and do it at scale, then we have to innovate and do better than we're doing today. So first of all, you know, I always think about how do we measure soil carbon? Of course, the gold standard is taking a soil sample into the lab, doing dry combustion. There are other lab methods for measuring carbon, which such as visible near-infrared spectroscopy and mid-infrared spectroscopy. So first, you know, we think about, okay, how are we going to measure our carbon? But there's more than that. Like so many times when I talk to non-academics, you know, they want to know, is it true that we don't know how to measure carbon, or that we're not good at measuring carbon? And I always think they're thinking about the lab, right? Like if I take a soil sample into the lab, you betcha we can measure soil carbon. But you have to remember, ultimately, we're taking this tiny, tiny soil sample and sticking it into an instrument, right? Of course, we know how much carbon's in that tiny, tiny soil sample. But the question is, how much carbon is out in that field or in the state of Iowa, right, in the soil? And even more important question is, how much is that carbon changing in the next 5 years, right? So those are hard questions. So when we're thinking about the harder questions, we want to know about, like, how do we spatially sample for soil? If we're going to take all these little soil samples, where do we go to get them? We know that soil organic carbon changes with management, and that change is smaller than how much carbon varies in space. And I don't even want to touch this bottom one. We're in Iowa today, so I think I can fairly safely ignore gravelly coarse fragment soils, but oh my gosh, what a headache. I don't even want to think about it. So I'm going to go on. So here's where we can grow, right? These are the hard questions. When we're thinking about landscapes and carbon change, what is the cost of measurement? And this cost is a balance between certainty and credibility. And the number one thing as scientists, as soil lovers, as agricultural lovers, we want to make sure that we are credible when we talk about change in soil carbon. The other thing that we need to think about, and you know, I'm talking to probably half academics here today, right, is scientist thinking. And oh my gosh, coming to the Soil Health Institute, I have been slapped in the face more times than I can think about being a scientist thinking, right? Like I think like a scientist. For 15 years, that's what I did. But I have to get out of that and think about commercial reality. And that has been a really fun challenge at the Institute, is taking all this great science knowledge that people like, you know, Marshall and Bradley have developed and published. Like there's such a wealth of knowledge, but we got to think about, like, how do we apply that knowledge commercially? The stories I could tell about that one. And then lastly, when we're thinking about commercial application of our knowledge in science, it's all about scale, 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 scale. And anybody who's ever measured anything in the natural world recognizes the hard component of scale. When you measure something little tiny, and it's got to represent something really big. So we have soil maps. We need to be thinking outside the paddock, the field, the farm. We need to be thinking more regionally and landscape wise. And also we need to recognize the outstanding technical support that we have in the field. That's one of the things I've recognized coming to Soil Health Institute, getting to work with more commercial entities and agronomists and people that are just making it happen. Oh my gosh, we are so blessed in our commercial nonprofit world in the United States of the outstanding technical support that is available to farmers and ranchers and soil scientists that are thinking like scientists and not thinking commercially. It's a great microcosm to work in, but we need to grow and we need to figure out how to leverage this amazing brain bank that we have in the United States. Okay, so let's just think straight about measuring soil carbon in situ. Here are the bits, right? We need to measure carbon, and we can measure it in the field, or we can measure it in the laboratory. We have to measure carbon concentration. We have to make some sort of volumetric measurement because we need to get to carbon stock, right? So a lot of times this carbon volumetric measurement can be kind of tricky when we're scaling up commercially. I'm not going to talk about that today, but just I want everyone to remember we have to do concentration and bulk density to get a carbon stock. And then there's this question of like, we'd really rather calculate carbon stock on a fixed mass basis, and we can actually do that quite easily. But the way the markets are going is on a fixed depth basis. And so we need to kind of reconcile the science and critically think about how we want to deal with carbon stock. I'm a big fixed mass basis person, but we can do both. It's not that big of a deal, and it's not worth getting caught up on, but it's just something to remember when we're thinking about what we're measuring. Now we need to think about where we measure, right? We have to have a sampling design. Random sampling, very statistically accurate. If you want to compare A to B, you do a random sample. We know in soil science, there's a little bit of science to sampling, and that we don't have to randomly sample. We can stratify our samples. And the whole idea of stratification is that we want to group our sampling into areas where we can get tighter and tighter variances. So we want to reduce our coefficient of variability within some sort of strata of soil, so that when we take 10 samples of the soil and 10 samples of this soil, we can separate them and keep our variance low, so we have that certainty and that credibility to our measures. And then that just like culminates all into this big question is how many measurements do we need to make, right? Balance, cost versus certainty and credibility. It's a big balance. So here's the big problem, right? Yes, we can measure carbon. This is a big soil carbon sample. This is a 3-inch diameter ring. We need to pull the sample. We have to transport it. It costs money. Once we get it to the lab, we have to process it, right? These are the big expenses, and getting out to the field. Once we're in the field, like I said here on the left-hand side, we know soil organic carbon varies spatially in the XY direction, easting and northing. But when we go deep, we also know, we know that soil carbon varies. So on the right-hand side, here's depth and carbon concentration. And we can see, obviously, this is nothing new to soil scientists or agriculturalists. But then the change that we're trying to capture, if we're lucky, is the difference between these two lines, between the solid dots and the open dots, right? This is the change that we're trying to capture, and we're trying to capture it out here in this field, right? A little bit daunting, but that's okay. I always say soil science to the rescue. And then this is the big part, right? We get what we pay for. In this balance of cost and certainty and credibility, you get what you pay for. So there are a lot of companies out there right now adding remote sensing and AI, and they say we can do it. We can have fixed costs. We can get it all remotely. We just have to take enough cores to train the AI. And that is so right. And I was in this conversation yesterday, and I'm thinking, this is such a blind way to do it. I like a little science and a little forethought. And I'm afraid that this remote sensing plus AI approach that's going on right now, you only know what you've measured, right? And if you take a complete AI approach to estimating carbon in space, You never know what you don't know. And there's risk involved in that. And that gets back to the cost, certainty, credibility. I'm not saying that one day we won't have enough data to do remote sensing plus AI to get really good carbon maps, but I don't think we're there yet. And we need to take a heck of a lot of samples, but that's okay. We can get there. And the way I think we're going to get there is thinking more of proximal sensing. So proximal sensing just means you're getting out of the atmosphere to sense the carbon, you're coming down to the ground, and you're sensing something associated with the depth of carbon. And of course, remember, we have to get concentration and the bulk density, right? So the nice thing about proximal sensing is our costs are fixed. You can go deeper. There is greater measurement error than the lab measurement. You can proximally sense in situ and ex situ. And I'm just going to talk about ex situ or in situ proximal sensing today because I don't have much time. But the idea here is either way we go, we're going to have to probably include both of these, right? I remote sense to figure out where to proximal sense. And probably about 10% of my proximal sense is I'm going to pull a soil cooler and send it to the lab because I want to know what I don't know. So we have this project funded by the Department of Energy. It's in the ARPA-E Smart Farm program. It's a big group of people. It's Soil Health Institute, University of Sydney, University of Nebraska and Lincoln, and a startup company called Yardstick. And essentially, we're looking at two different proximal sensing modalities: data acquisition, modeling, estimating that carbon stock, and ultimately coming in with optimized spatial sampling plan. My point here is that this is a highly integrated approach. All approaches are going to be highly integrated. It's actually not as easy as it seems, even if all these different little pieces work really well, and they do. The problem is getting them put all together and keeping a robust system so that, again, you get out of the scientific thinking and into the commercial thinking. These things have to kind of be bomb-proof. And this is the problem, right? So this is just a model of carbon stock change. And if we think about if we can measure carbon stock change, here's two probability density functions. And essentially, the more uncertain we are, we're losing money, right? When we're got to sell a carbon credit. And this is the big trade-off. And so we did a little simulation with our Smart Farm project. It was by the University of Sydney. Let me check my time real quick. Doing okay. There's a lot baked into this, but I didn't want to just give you results and tell you something without kind of giving you some background of what we did. So we looked at 3 sample site selection methods. So we're trying to integrate everything. And there's random sampling, which is kind of the statistical norm if you don't know anything. There's stratified random sampling, what I mentioned before, and it's pretty much the state of the art today. But the question is, how do we want to stratify random? We could use in the United States, we could use our Circo maps, or outside the United States, and we're testing it in the United States, we could use another algorithm called OzPATS. And what OzPATS does, it's a little bit different. It decides where to sample, not just on stratified random, but it's got an optimization function that's trying to optimize for cost, location, and spatial variability all at the same time. And in particularly, we have changed the OzPATS to estimate based on the sampling certainty. So the big question that we had is, what if we have laboratory-based measurements, right? More expensive, more certainty, versus in situ Vis and IR samples, less expensive, more uncertain. And what if we had just a fixed auditing cost of $10 an acre? So what do we do there? So we only were able to simulate for 5 fields because we need really high resolution carbon data. I think some of this is from Iowa. And the important thing here is if you look on the 5 sites, we have lab versus deep sea, which is the Vis and IR in situ measurement with the higher uncertainty. So we're taking about 3 times the number of samples with the deep sea, but we're not having to haul anything to the lab. And if we look at the 2 methods for using stratified, so here are the methods: random, Circo stratified, OzPATS stratified. We find that when we use the in situ measurement and we're taking 3 times as many samples, we're not hauling any samples to the lab, but we can, this is our mean uncertainty, we can keep our uncertainty very comparable and even better to laboratory measurements, even though we have more error in the measurement. So this is really just bringing home this concept of proximal sensing. You don't have to be as accurate if you can take more measurements cheaply. And that's essentially, this is really what I wanted to show you. So we did these simulations for a fixed auditing price, and we found that in situ measurements, even though they're more uncertain, they outperform the lab in getting that credible number that we need at the end. For sites with low carbon stock variability, there was really no difference between any of our methods, but sites with greater stock variability, the stratified random outperformed the random sampling. And of course, we need more fields. So I put out a call if anybody has high resolution carbon stock measurements across fields, so that we can do a better job of testing OSPATs versus Sergo, but they're performing about the same in the fields that we have today. I did want to acknowledge the specific team that delivered that information. It was primarily Alex McGratney and Ed Jones, but our team at Yardstick is really pushing us to ask the questions to get us out of scientist thinking and into commercial thinking. Yeah, I think with that, I just thank you. I know we have a nice panel discussion and I'd like to get on to that. So.
Great, thanks for that fantastic presentation, Christine. So we'll have a few minutes for clarification questions, and then we'll move into the panel, and I'll introduce the panel at that time. And I think we're doing the questions through the chat, or maybe Kalina will help me out as well. I see one question, I'll read it for you so you don't have to open your chat, Christine. Dr. Morgan, does this data include both organic and inorganic carbon? How to discriminate organic and inorganic carbon when we use NIR measurements?
Great question. Of course, it's just organic carbon. If our soils are calcareous, one of the nice things about VisIR is it measures inorganic carbon better than it measures organic carbon. So we can differentiate with VisIR, MIR. I think, in fact, I don't know if Sky will talk about this, but I mean, there's evidence from the Lincoln lab that MIR is the preferred way to measure inorganic carbon over the traditional method, acidification methods. But anyway, yes, we're always dealing with organic carbon. Okay, I see the next question. You want me to just take it, Marshall?
Sure, yeah, go for it.
Okay, this is from Sarah Carlson at Practical Farmers of Iowa. It says, Christine, can you explain why there is not an option for fixed mass at lower depths? Was that because of the cost to go deeper, or could you tease out a bit more about that difference you mentioned? You know, Sarah, I'm not completely 100% sure why we're not going with fixed mass. Maybe somebody else knows. I think it's just kind of you know, the markets are going to determine what they want. And I think they just decided that the first thing they wanted was 30 centimeters. And even the 30 centimeters kind of came from FAO. If you read their big bulletin on carbon measurement, I think it's just been a compromise of, like, you know, it is so much easier to tell someone to go dig a hole of 30 centimeters than to go, okay, here's what you got to do. You got to do 2 holes, and then you got to look, you know. I think it's just that scientific to commercial translation. And I think, like, if we are working with our penetrometers, we can do both. It's not really that big of a deal. It's whatever anybody wants. I don't know, Marshall, do you have any more insights about that? I've never really thought about figuring out why it is.
It's a practicality thing. I really like how you put that scientific thinking to commercial thinking. Stephen Hall has a question. Do you want me to read that one?
Oh, I'll get it. Okay. Could you describe more about the in situ method quantifies bulk density? Okay. If you're in situ carbon stock uncertainty driven more by bulk density measure or the carbon concentration? I'll start with the second. Bulk density varies a lot less across the field than carbon concentration. And when you look at their magnitude of variability, carbon concentration is the one that's most important to get. I kind of think, we haven't done the simulations, but I always joke around with our team. It's like, I think a good pedologist could wing the bulk density. What do you think, Bradley? Sounds like job security to me.
But you're right. Yeah, field experience, and you can pretty much get it close enough. And the great point about the uncertainty. Where is the most uncertainty coming from?
Yeah. So our sensors are measuring bulk density. So I didn't talk a lot about them, but the sensor modality that we have that's on the back of a four-wheeler that you have to use hydraulics to push into the ground, it's using penetration resistance. And we're combining, when we do Vision IR, we're also measuring with Vision IR the water content and the clay content. And so you can make a pretty robust pedotransfer function that takes penetration resistant water content and clay content and predicts bulk density. With the handheld that's being developed by Yardstick, we're also measuring the bulk density, but we're measuring with torque rather than penetration resistance. The next question, Marshall, just stop me.
Yeah, we've got time for one more.
Okay. Have you looked at streaming solar organic carbon sensors like Smart Firmer from AGCO or iScan from Veris Technologies? I am familiar with those technologies. There's reasons why we have our own, but a lot of them are based on similar physics. It's just about having equipment that, gets you what you need when you need it, how you need it. All right, Marshall, back to you.
Great. Yeah, that's perfect timing. I think we'll save more questions for the panelists. So at this time, I'd like to introduce our panelists. We've got 5 friends and colleagues. Dr. Bradley Miller, he's a associate professor here in the agronomy department. Dr. David Laird, he's a professor emeritus from the agronomy department and co-founder and president of InSense. Kelly Nascimento Thompson, a graduate student in Ag and Biosystems Engineering here at Iowa State. Lance Gunderson, the president, co-owner of Regen Ag Labs. And then Nigel Rule, assistant professor of chemical and biological engineering here at ISU as well. Welcome, panelists. And we'll just go around, and if you, we'll try to stick to maybe 2 minutes each and just provide some thoughts on Dr. Morgan's talk and maybe any questions too. We'll kind of moderate a back and forth here. We'll start with Bradley. I'll pick the order.
All right, good morning, and thank you for having me, and thank you very much, Christine, for kicking us off with such a great presentation. I was really inspired by how you framed the whole question, because certainly there is this balance between all the details of the science and dealing with uncertainty, and then bringing out to something that is really scalable and practical for the commercial world. And really, you kind of gave me quite a few things that I can kind of drill in on. But one thing is, everyone thinks about the soil stocks. I think it's really important to think about the soil as a three-dimensional entity, and that there's a lot of components that are a lot more mobile than we might want to think about. So I think there's a lot of temptation to do repeated measurements at the same location. But the real challenge with that is maybe that carbon shifted in location. Maybe it slid downhill a little bit from some process. So we could easily get measurements that show decline in carbon, even though it never left the field. So really, for full accounting, we kind of have to think of that whole three-dimensional body. And that kind of lends to the mapping that you were indicating. I also want to think about how this, if we're going to scale up to the field or bigger areas, really we're dealing with some type of prediction. And so we really have to think about not just measurement uncertainty, but the prediction uncertainty and how we're doing those things. So in all of that, we're managing uncertainty. So when we're dealing with managing uncertainty, we have to communicate with investors about what that uncertainty means. And I think at some point, we're going to have to kind of have a threshold where say, okay, we're not completely certain. We haven't, not 100% sure, but maybe a 69% chance that that change actually happened. Maybe that's good enough for the intentions. So when Dean Dan kind of indicated the intentions, I think maybe that might be kind of a piece of dealing with that uncertainty. And I think one more piece, because we're dealing with so many kind of multi-part system. We need the measurements, we need the upscaling. All the different pieces are contributing their own part of uncertainty. And a trick for all of us scientists is we all want to be an advocate for our part of the system. So we'll kind of wave our hand and say, hey, invest in our part. Don't worry about those others because my part's the one that's going to solve the problem. And I think because it's a multi-part system, there's not going to be a silver bullet. So we kind of have to find a way for us to all to work together to get the whole system as low uncertainty as possible without necessarily cutting each other down, because it takes one of the earlier comments before this conference started was it takes a village. So it's really going to take a lot of different pieces working together and to make it all work.
Thanks, Bradley. Dr. Laird, you're up next.
Thank you, Marshall. And I want to give a special shout to Christine. That was an excellent presentation. Really appreciated the coverage and the challenges that you've laid forward. So I also very much appreciate the challenge of moving from an academic world into a commercial world, because that's what I'm trying to do personally. So I realize that all of my bright ideas as a scientist don't necessarily work when you try to open a new product, start a market. I thought I would just add a couple of points that I think will supplement some of the comments that Christine and now Bradley have already made. And the first of these is modeling. As Christine said, we ultimately have to measure the soil carbon content or stocks in our soil and understand the spatial distribution across the field as a function of depth and ultimately as a function of time. And yes, that's true. But from my perspective and from a farmer's perspective, it's going to be extremely challenging and extremely costly to build a carbon credit program based on measurement. I would personally support carbon credits based on practices which can be easily documented and can be easily supported. But behind those practices, we need the measurement and we need the modeling in order to validate those measurements. And that's where where I think this comes in, because from a cost perspective, to get the quality of data that we need to write a check for a given carbon credit in a given field. If we do it based on measurement, I don't think we'll ever be able to cover the cost of those measurements. So we need robust models. We need robust measurement technologies. And I would very much agree with Christine's perspective about the in situ sensing technology. We've worked in the past extensively with near infrared, and we're currently working with mid infrared sensing systems in soil, which measure both carbon, water, and you can use a probe that will simultaneously give you penetration resistance. So that technology is there. The pedotransfer functions are there. They're not always as robust as we'd like, but they can be improved iteratively with time. And that's what we need then, is a nationwide, but region-specific auditing, calibration, validation system that builds that model. And I think going back to some of the work that Bradley does, we can relate that, use a modeling system that looks at the landscape and different spatial positions within the landscape, because we know that's where there's a significant amount of variability in carbon stocks as a function of those landscape positions. I want to add one other challenge that I don't think has been mentioned yet, and that is carbon quality. We know that fresh biomass is part of that soil carbon stock, but it has a half-life measured in weeks or months. We know that particulate organic matter is a component of those carbon stocks that may have half-life in a year or two. And clay-associated humic substances may have half-lives of decades. And condensed aromatic carbon can have half-lives of millennia. And so some assessment of quality needs to also go into our modeling effort to be able to accurately predict and understand the temporal variability of carbon stocks as well. And with that, I think I will pass the torch and again, thank the team for this opportunity, and be happy to try and answer questions.
Thanks for that, Dr. Laird. Kelly, you're up next.
Good morning, everyone. I appreciate the invitation to be part of this panel, and it was a very good presentation to watch. And now, since I'm a third-year PhD student, I guess I'm mostly involved with the scientific side of things. So it was good to see that perspective of thinking about the commercial reality and how that can impact modeling of soil carbon. I am studying remote sensing, so I would arguably vote in favor of using remote sensing for soil carbon estimation because that has been my experience so far. But it was very productive and important for me to learn today how they have this the sensors that they use in the field. So one question that I have for the panelists, for the keynote speaker, is about what limitations she found using the GSORGO data, because your results indicated that OSPADs performed better than GSORGO. So what were the limitations from the GSORGO database? And yeah, I have this question to finalize my comments.
Okay, maybe we'll return to that. Do you want to return to that after all the panelists? I think I see Christine nodding her head. Thanks, Kelly. Dr. Rule?
Yeah, so thank you, Christine, for that wonderful talk. As a person who developed sensors and also someone who came from industry and still keeps his foot with lots of projects as well as startups out in the space, it's always great to see this interface. So really appreciate your comments. Two things that I wanted to riff on that I thought were very well put. So one, there is a lot of this efforts in remote sensing and building models, but you mentioned there's still an extreme need for measuring. We can't fully rely on everything, not having no contact, right? We need to have some methods of contact. When I worked for DuPont, actually my first times here in Iowa, we're down with Pioneer, and there's large efforts, right? Because there's only so much you can get from remote sensing, and there was a lot of work we put into doing under canopy measurement. So glad to see continued work in this space. And the other thing I really liked was your comment, you don't have to be as accurate if you can measure cheaply. And the reason that resonated is we build sensors, and our push is for extreme low cost, and that comes with some limitations, right, in both of accuracy as well as duration. But if you can get a larger data set and use that data set as a holistic picture, and that gives a better view. And where that kind of echoes is we did projects as well with diagnostics, and we're all aware of SARS-CoV-2. And it was similar with COVID, right? If you can take more measurements, and maybe they're not necessarily as accurate, but if you can take more of them more frequently, you actually get a better picture than if you just take one better, more accurate measurement. So anyway, appreciate your comments and look forward to continuing discussion.
Great. Thanks, Nigel. Good points. And last but not least, Lance.
Good morning, everybody. And, I want to echo what everyone else has said. Really appreciate the opportunity to be here. As somebody who operates a laboratory, I will absolutely say this whole carbon thing has been an absolute nightmare and a giant mess. I was involved with 19 of the original 26 carbon market groups out there. I think I received a 136-page document from Climate Action Reserve regarding QA/QC procedures, et cetera, et cetera. So I welcome anything that Christine or the others on this group can come up with as a solution. And I'm not here to say that everything has to be measured. Please do not send me 1.5 million soil samples to analyze carbon. And I've had that request. And you're right, it's difficult. The dry combustion equipment that's kind of the gold standard is not cheap. It is not high throughput. But as Christine pointed out, can we measure it accurately? Yes, we can. These methods were not new, right? They've been around in soil science for a very long time. But simply, having companies say, we want to send you 1 million samples and we expect to have them analyzed for $2.50 to $3 a sample doesn't work when your per sample cost is $6.50. So, we've got to have better solutions. I do think that obviously we need some measurement piece, and I'm not saying that necessarily wearing my business owner's hat. I'm saying that just because as a scientist, I think that we have to actually take some measurements. Now, whether we develop really solid remote sensing technologies, and I know that there's a lot of effort being put into that, obviously, from a lot of groups, that's okay. That's great. But yeah, it's a very difficult challenge. Obviously, anytime we're measuring sample depth is incredibly important. For anybody who's gone out and pulled soil samples, I can't tell you how many times I get a 6-inch sample, but the probe could only go on the ground 4 inches. Right? I mean, and that happens. And so that's one of the other constraints around this, is because if you're building models off of that data that's coming out of any lab, you're only as good as the data coming out of the lab, and the lab's only as good as the sampling procedure, et cetera, et cetera. Toss in the idea that a lot of these sampling companies use lubricating oils on probes. If you've ever tried shoving a probe in the ground, I mean, I just had that call yesterday, WD-40, vegetable oil. There's a lot of moving parts here, right? And so that's why I said for me, it's been a nightmare, because I get those questions all the time and honestly don't know. In my previous 17 years of working in a laboratory, I'm guessing we analyzed 2,000 organic carbon or dry combustion carbon samples, 98% of which came out of university systems for research. In 2020, I ran just over 60,000 dry combustion carbon samples, and that we did all of that from August 1st until the end of the year. So in 4 months. And obviously there's still a big push out there for that. So I'm open. I mean, I like this discussion. I wish, much like most science, right? We usually are trying to catch up because the cart gets shoved down the hill and then we're chasing the cart. But we're doing the best we can from this side of things, and very interested in MIR technology and any other type of measurement technology. But again, we've got to consider the entire process. I know MIR was incredibly promising when I saw it. However, the limiting step then became grinding, sample processing, right? So planetary ball mills, things like that, where now your bottleneck is grinding 200 samples a day, not analyzing 200 samples a day. So very open to ideas, and we're very on board. And Regen Ag Lab is trying to, obviously by the name, I've been involved with this for 12, 14 years. And so, as a business, that's what we're focused on.
Thanks, Lance. We appreciate that. There's a few questions in the comment box, but I want to return to Kelly's question. Kelly had asked if, and correct me if I'm wrong, if I'm paraphrasing it, Kelly, but the kind of the limitations with Surgo versus OSPATs, and I think she had asked about what problems you had with Surgo.
Oh, yeah. I think our biggest, there was no problem with Surgo. Surgo performed as well as OSPATs. What's in OSPATs is Polaris, which is a product that's made from Surgo. So they're very much the same thing. Polaris is just kind of dealt with some of the inconsistencies, I guess, with Surgo, and then also provided to fill in a few spaces. So I think that right now they're very similar. The benefit of OSPATs is the optimization function that allows us to set prices and costs and figure out and see then how the sampling design might change. So that's kind of like, you know, the number one thing any company asks for is like, how many samples do I need to take? They never ask where to take them. That's the second question. The first question is, how many do I need, right? That's where, you know, the soil science comes in. And so my point is OSPATs actually uses Surgo. It's just that Surgo doesn't produce another map of uncertainties. And to optimize the sampling function, you need an uncertainty map as well as the map of the actual entity that you're trying to do. So that's kind of where Surgo has a current limitation. Oh, and I wanted to say, because Nigel brought up the point about cheap sensors. I'll use a cheap sensor any day, as long as I know that the calibration of that sensor doesn't have bias. And that's our big thing, right? So if you just go back to the old days of learning your statistics and you learned your first, you know, normal distribution curve, what we're trying to do is we're trying to predict that mean. And so you can use a lot more samples to get the mean, or you can use 3 samples to get the mean, right? But the important thing is if you have to use a lot of samples because, you know, you have to take a lot of measurements, the central limit theorem will get you to that mean. But if there's a bias, you're in trouble. So that's the main thing that we just need to really work on with sensor design is bias. And I think Ross Brickelmeyer asked a really great question about where proximal sensing is in the registries. That's a great question, Ross. I think that's a really good question for Chris Tolles, our partner at, or I don't know, maybe David knows. I don't think that there's been in much application of proximal sensing to the registries. Do you know, David?
Not that I'm aware of, but I haven't paid close attention. So
Yeah.
I would agree with you. Proximal sensing is the way to go for, but it's not the only thing. We've got to have the cores to calibrate the proximal sensing.
Agreed. I think that's probably, you know, I don't think any proximal sensors have been ready to bite off the registries, because one of the things we're really working on in our proximal sensing is making sure that as we move across large areas that the bias isn't there. And again, like I said, like, I think this is, for me, this has been this is my Achilles heel, right? I'm a scientist. I probably don't let go of things soon enough, you know, to let it hit the market or let someone in the market deal with it. I'm constantly like holding on to it going, wait a second, we don't know this yet, right? And that's actually why I love working with Yardstick and actually other companies that we've worked with. It's just like, they're like, you know, Christine, whether you know it or not, someone's going to have to go ahead and get this done. So, you know, you're either in or you're out. And that's just, you know, that's just the practicality of that commercial world. And I'm sure David has had a lot of those am I in or am I out conversations too.
I'll just add that bias can come from the sensor itself, but it can equally come from where the samples are taken.
Yes.
And the ability to accurately sample a complex landscape is hugely problematic. And maybe Bradley would like to dive in on that.
I would say 100% of the bias comes from the calibration, right? Like it's what you give it to learn. But go ahead, Brad.
Well, you hint at it with the stratification. I mean, in the modeling, we call it the feature space, but trying to capture all those different conditions on the landscape. And Surgo certainly provides, I mean, that's kind of what they were doing. But now we have additional things from LiDAR and other remote sensing that, and I think it's kind of key to note that you're using Surgo as a sampling design, not necessarily the attributes from Surgo. So that, the real key is to know what are all the varieties of environments that are out there, so that when you calibrate, you're getting all of those differences.
Yeah, my big fear with AI, and AI is used in calibrating proximal sensors, it's used in calibrating remote sensors. My biggest fear is when I hear someone non-soil scientist, non-agronomist calibrating AI, and I'm just like, dude, like, I know what you don't know. You don't know what you don't know. And that model certainly does not know what you don't know. And that's the part that frightens me. And that's again, like, for me, it's this tension between commercial, you got to get out there and get something done, because today is when the answer is needed. And you just got to do the best you can. And the scientists, like, right, like as scientists, our biggest fear is not knowing what we don't know, because that's when huge mistakes happen.
I'll also add that there is a problem in that different commercial entities, let's call them carbon credit marketers, are using different protocols, and associated with those are different biases, and there's real dollars associated with those biases. So we all, I would argue that the NRCS needs to step in with a gold standard, and then all the commercial companies could calibrate against the NRCS. That hasn't happened yet, but I think that is something that will really help bring the carbon markets and the laboratories trying to quantify carbon credits and carbon stocks under control.
You know, Dave, we did something very interesting. I share this. I think this is something that at least the soil scientists and Lance would be interested in. We sent a couple of samples. Like, I was really worried about sending soil samples to commercial labs for carbon, because I was worried about the grind, right? That it's a 2 mil grind. Is it a good grind? The number one thing we found out is that the labs were not doing a moisture correction. And it's okay if they're not, actually, it turns out it's fine if they're not doing 105-degree moisture correction. But most of the labs, QA/QCs, are like, we get the sample, we let it air dry for a little, we grind it up, and then we do the carbon. And the biggest error was coming from the fact that the soils weren't even, dried at 60 degrees C. And all the error was not coming from the grind. It was not coming from that oven dry to like air dry moisture correction. It was coming from the variability of air dry. And, you think about different humidities, different labs capability when you lay a sample out, how long it takes it to dry. And I thought that was interesting because, again, in my science brain, I'm all worried about like, oh, the hygroscopic moisture, and I'm worried about the grind. No, it was something super, super simple, like, how'd you dry your soil?
Yeah, that's really a critical part of that quality control. This is also, I'll give a plug for near infrared, because you can work with field moist samples, and you can get both water and carbon content. Now, we did a study, I don't know, 2 decades ago, I think, comparing the accuracy of carbon measurements, air dry or oven dried versus field moist, and you do lose some accuracy, but it's a trade-off between the number of samples and the quality of that data, and I think in reality you're better off by taking more samples and just running them field moist with the near infrared system.
Yeah, if I ran a commercial lab today, I would have VisinIR, and I would get the samples in and I'd just scan them as they came into the field. I would just put a contact probe on them and scan them.
And maybe 5% you take out for the thermal combustion.
Yeah, right.
QC.
Keep your calibration good. Yeah, that's what I would do too. But the big money still is, and you got to get that bulk density sample. And that's why I've really gone to in situ, because for a while I thought, oh, the trick is just to get the labs faster, like Lance was saying with MIR or Viz and IR. But I think ultimately, that's maybe a small Band-Aid on a big problem. And the big problem is we just can't be shipping so many soils to the labs. But I agree, like, even when we do our cost estimates, I'm again very conservative. I always estimate sending 10% of samples back to the lab. But man, like the volume some of these carbon developers are doing, you could probably send 2% of the samples back to the lab. I mean, because the volumes are so huge.
Have you tested the pedotransfer function for bulk density using moisture and penetration resistance in diverse soil types, landscapes? Because
not yet. That's one of the things that we're doing under this DOE, and that's really our next 12 months of work.
I worry about hitting a small rock on your penetration resistance as you go down, and how that's going to bias that data.
We can see those, like you can see the rocks, et cetera, and I think you can pull those out.
I see a big rock, but what about a little rock?
Yeah, we can see that. My biggest fear actually is just being able to consistently push it into the ground, like with a constant force. I think for me, that has been my biggest like headache. But no, we'll know more probably in about 12 months, because we just need to get out and just push this thing in the ground in places, I think we've tested in Illinois, we've tested in Nebraska, but we totally need to get out and about. Yeah, it's still a question.
If I can make a quick comment. So yeah, Christine, you brought up the point about the drying. So if you really want to know what causes you to bang your head against your desk, it's that the current SOP for dry combustion carbon is air dried soil, and air dried meaning, you can use heat, but obviously at a temperature lower than 105, right? But bulk density requires you to dry at 105. And the funny thing is I have been arguing with the powers that be, whoever they might be, and I don't know who decided they get to be those powers, but they say, no, you can't do that because it alters the numbers. And while that is true for conventional analysis of like potassium, for example, right? If you dry a sample at 105 degrees C, you open up the clays, you're driving off the hygroscopic moisture, et cetera, et cetera. And then they say, well, you can't use those samples to analyze carbon according to their methods. And I'm going, so let me get this straight. We're pumping these soils into a furnace that's 1300 degrees centigrade, but yet 105 degrees C is going to blow the carbon off. It makes zero sense whatsoever. And no matter how many times I try to point that out, nope, they have to be air dried. And so, I mean, and again, if we want to run the samples, like I see the problems with it, and I'm not even a soil scientist, I'm a biologist, but I can point out those things. And then the interesting thing is that nothing changes. So that's why I think some of these middle companies, the carbon market companies that's why they have so many different takes on how to do this. And it's just like I said, it's an absolute nightmare. Because now we're pulling separate bulk density samples. They're dried at a different temperature, and you can't grind them and run them for carbon according to the protocols that are out there, right?
Lance, that's real problematic from my perspective, because the type of clay, the texture, sand, silt, clay percentages is going to influence the hygroscopic moisture at an air dry or whatever moisture until you get to 105. Then they converge pretty close to the same number. So if you've got
I agree 100%. Like I said, I've been trying to point that out for 4 years.
Good luck. Go for it.
Yeah, right. But the thing is, at the end of the day, they say, well, do you want to run some samples? And I'll be honest, as a new company, yeah, we're more than happy to run samples. And they tell me how they want them done, and that's how we do them. And we can get very repeatable numbers, but again, our repeating something that's incorrect is not necessarily making it better, right?
So
I agree with you.
So David, I think the point here is, I think this is a good point because I've thought about it too. Soil science, in a lab, we always air dry our soils to do any analysis, right? Because, the clays could collapse or something could happen. But carbon, as I understand it, is actually okay to dry soil at 105 and then put it in the furnace to measure carbon, right?
Absolutely.
And it is in some of these protocols that you can't measure carbon on something that's been dried at 105. And I think that has been a mistakenly interpreted thing, because in soil science, I certainly would not do particle size on a soil that was dried at 105, especially in the state of Texas. And I think that it's been mistakenly interpreted that you have to air dry soil to do any soil analysis. So carbon must be included. And it seems to me that would be something pretty easy to change in the carbon registries.
I don't know who the powers that be are, but perhaps scientists need to get together and say, wait a minute, this is not a rational protocol.
Right. I think that, so Lance, I think that actually is quite easily fixed. I think you just need to get, the right ear and just get it edited.
Right. Well, as the soil scientists in the room, and I'm not pointing the finger at myself, look, I'm the off the wall eccentric quack who is a soil biologist running a soils lab. And so, a lot of these groups, they have a science advisory committee, and they have all these soil scientists out here. And I think you're exactly right. The soil scientists are taking that kind of conventional paradigm of how you test soil, and you don't dry them at 105, and they're applying it to carbon.
Yeah.
The common sense side of me says, well, wait a minute. Loss on ignition organic matter is done at 360 C, up to 500 C, depending on where you're at in the country. Dry combustion's done at 1300 C. I mean, there's no way 105 is again, you're measuring total carbon, or total organic carbon. So you're not driving this off. So it's very interesting. I've tried. It's going to probably take somebody with more clout to convince, whoever it is, Climate Action Reserve, et cetera, to really listen to that. It does create a potential back end problem. I will admit that. So if the samples are coming to the lab in large volume, we're a relatively small outfit here compared to some of the big players in the ag testing game. But we can air dry 10,000 samples a day. And we can do them overnight. If I have to install the same number of ovens to oven dry 10,000 samples at 105 degrees C, that changes the game a lot. I mean, my electric bill goes up to $5,000, another $5,000 a month, and I got to buy 70 $10,000 ovens. So, I mean, and that's true of any large, so it does create, it is better. I'm just saying that does create another issue unless we continue this discussion of, well, how do we get fewer samples coming to the lab? Again, 5% of the samples going to a lab to represent 100 million, 200 million acres is still a lot of samples.
Thanks, Lance.
Certainly can't do it on 200 million acres.
Sorry, yeah, we're getting close to our end time. I just want to make sure our other panelists don't have any further comments. There are a bunch of questions in the chat as well. Kelly or Nigel, Bradley, any opportunity for any comments before maybe I pick out a few of the questions? My co-host here has a question. I might pick her question next. We've got a whole host of them on here.
I'll jump in just really quick. So a natural conversation is really focusing on the chemistry, and it's absolutely important. But I just want to kind of point out that the error from the chemistry part is just part of the system. So it's very easy for us to kind of spend hours talking about lab methods and the very fine point detail, but if it doesn't have a way to scale up beyond that point data, there's going to be some issues. So it is more than just the chemistry, not trying to de-emphasize chemistry, just point out that it's more than that. Another interesting thing about lab analyses that I think is, for accuracy versus repeatability. So even maybe a little bit about the bias, the main thing is to have samples that are comparable. So, does any lab measurement really get us the absolute truth? And that's kind of a hard pill to swallow sometimes, but really what matters in looking at carbon change or just being able to compare one location to another is, are the methods comparable so that it's repeatable? We actually say there really is a change. So maybe it was 1.1, maybe it was 1.2, but at least they were consistently, so maybe there's a bias, but it was consistently biased, and then it's still comparable. And that may be a nuance that we want to kind of keep in mind.
Thanks, Bradley. Kelly or Nigel, any final thoughts? Before I ask Lisa's question.
Mine is just an obvious one, that this is definitely a problem that needs multidisciplinary attention to it. So, I'm always a fan of thinking outside the box of, if sampling is an issue and drying is an issue, how do we get around those by measuring it approximately in the actual location, and, what other new technologies can be employed on it. So anyway, it's my obvious point.
So I have one last question. Since the discussions seem to be more focused on the field sampling, I'd like to ask if they think that the keynote speaker thinks there is a way that remote sensing can help us reduce sampling, the field sampling.
What was the question again?
So can remote sensing help us reduce the field sampling?
I think remote sensing is the source of how we stratify our sampling. And it's also going to be that in covariate of how we interpolate our sampling. I mean, we use it already a lot. We use remote sensing, and, our terminology is there, it's a covariate. And ideally, we want some sort of high resolution, low quality piece of information for every covariate that we think is driving carbon distribution. I think the trouble with relying completely on remote sensing is that we don't know what the management history is, right? Like how that soil has been disturbed and how it's been used greatly affects the carbon profile with depth. And if you don't have that information, you can make some very bad mistakes, right? Like if you have two fields and remote sensing wise, they're exactly the same, but one's been moldboarded for 3 years or for ages and has been in no-till for 3 years versus the other is conventional for ages and now in no-till, they're probably going to have very different carbon profiles with depth, but they're going to look the same on the surface. David and Bradley may want to add something, a better example than I just did, but anyway, that's the idea.
We'll have to continue the conversation via email or in the chat box. Thank you all. This has been a great discussion. And we're going to take a 10-minute break and come back. And my co-host, Dr. Lisa Schulte-Moore, will be taking over. And we'll see you in 10 minutes.
All right, welcome back, everybody. Thanks everyone for tuning in today. Again, happy birthday. For those of you that don't know me, I'm Dr. Lisa Schulte Moore. I'm a professor of natural resource ecology and management here at Iowa State University and co-director of the Bioeconomy Institute. Excited for the discussion today. It was so great to hear that interplay of the main speaker and all the panelists and the questions in the chat. Keep it coming. This kind of discussion is really what helps me learn, is when we get these experts talking to each other and questioning each other and riffing off each other. And then also the audience bringing in additional understanding and questions. So great, let's keep it up. Let's see. One thing I want to say before I introduce our next speaker is stay tuned to the very end. The ISU and the Bioeconomy Institute have a very exciting announcement to share at the end on this Earth Day. So I'll just add that little bit of mystery here to keep you all engaged. And with that, it's my honor. I'm really excited to introduce our second keynote speaker, Skye Wills, Dr. Skye Wills. And it's special for me for a couple of reasons. Skye is obviously an incredible expert. She works for the USDA Natural Resources Conservation Service. She's the national leader for soil research at the Soil Survey Center and has done amazing things in terms of programming with the National Cooperative Soil Survey Program, research branch looking to develop new techniques in dynamic soil surveying, including looking at soil health, soil moisture, and other properties, especially with this need to look at change over time and more rapidly as well. Her work includes the Rapid Carbon Assessment Project, and she's using the Dynamic Soil Properties for Soil Health Project as a way to move that forward. Skye is a proponent of reproducibility as well as open science to maximize the impact and accessibility of soil data. So while the first panel, we really wanted to focus it on innovation, this one was more focused, this panel and question is more focused on implementation, but I think we saw in the last one that these two things go hand in hand, and we'll learn about that as well here. Why is it special to introduce Skye? Well, my very first semester here at Iowa State University, as a newly minted assistant professor, Skye's PhD advisor, Lee Burris, a soil scientist here, was my mentor. And so I was able to meet Skye my very first semester here, met her working in the soil lab toward her PhD degree. And it's just so cool when you see young scientists really grow and then move into leadership position, and at the national level in this case. So welcome, Skye. We're just so excited to have you here today. And yeah, thanks for all your work.
Great. Thanks for the introduction and thanks for having me. Yeah, you probably met me measuring soil carbon because I think I've been doing it for 20 some odd years now. So it's always hard to be a follow-up speaker in these things because I think of all these things. I'm like, oh, I should have done that differently, or maybe I should have left that part out because Christina already covered it, or, it's just, so if I repeat something, I apologize, but I actually think our talks are going to go together pretty well. And in listening to Dean Robinson's conversation earlier and saying soils are infrastructure, I actually often say that soil survey is infrastructure. So maybe what it should be is that soils are infrastructure and soil survey is the map. It should be and it is the map that we have on Google, right? We can use it like that. We can use it as a way to guide our activities and, just let us know what we're doing a little better, both on the front end in the where to sample, in the back end, how to interpolate and extend, which I heard some conversation about. So I'll try to touch on those items just a bit. So as Lisa said, I am the national leader for soil research in the National Soil Survey Center. And so I'm going to put up a picture of a block diagram that I just happen to have. I don't even know what talk this is from, but I thought I'd let you look at this while I talk about what soil survey is. We cover the whole country. Obviously, I'm sitting in Lincoln, Nebraska right now, but Iowa is part of the area we cover, and a part I know pretty well, obviously. But we really cover lots of different areas, and we kind of think of them as rule sheds sometimes. And I think Bradley and Christine and some others have all mentioned that we really need to think about what we're measuring, what are rules that we develop, whether they're models, whether they're just, algorithms that extend what we've measured, whatever we've trained our machine learning or AI on. We need to think about what that really applies to. Where did our stuff come from and where should it go? And so in soil survey, we've really applied these conceptual models across the country that can be used for all kinds of things. And if we think about how carbon is moving on this landscape, just general background knowledge tells us, things are starting at the top and maybe moving downhill. We've also got water shedding and water accumulating areas. So you have different amounts of carbon being produced through biomass and different amounts of carbon being respirated or, just lost to the atmosphere. So anytime we're thinking about, okay, now I'm going to put a field on this and I'm going to need to superimpose both past and current land use, then I'm going to figure out what my current soil carbon is. And then I need to figure out either what it used to be or maybe multiple possible scenarios. So now we're kind of into a multiverse. So soil survey, we think of as this, one thing. We've described this block diagram, we've said what's there, we've mapped the soils. The pedologists of Iowa are, top notch. There is no place on earth that is mapped better than Iowa. There just isn't. And we still don't know everything. We don't know how this will change when we apply practices. We have some good ideas and we can make some pretty decent guesses, but it's really hard to bring all of the pieces together. And I think, as my pitch in the intro was, I think our only hope for doing that is having really good standard data and then making things compatible so that we can all work together. So supposed to talk about measuring soil carbon. I think Christine covered a lot of this already, but I think it's worth mentioning. I find this a lot in NRCS. A lot of our soil science expertise is as much agronomist as it is soil scientists, and they have come to me for advice and be the technical expert on what should we do to measure soil carbon. I'm just like, well, it's not like most soil tests. And really the thing that's important and we're talking about today is carbon stocks aren't like most soil tests. And when I think about most soil tests, I think about what most consultants, most of the infrastructure that exists for soil testing in this country, not all of it, but most of it, is developed around fertility tests. There was a lot of work that went on in the 50s, 60s, 70s that figured out how we can test soil carbon, how we can test soil fertility. And sometimes carbon was done as part of that, but not usually. You're really interested in what's happening in the surface and then how that's going to tie to production. So almost every state has a good extension office. Iowa State has excellent resources about how you can take samples for soil fertility. This is a particularly good reference that I've used to tell people, this is how you go take a good soil fertility sample. And it can tell us some things about how we might want to do it for carbon. And it's really focused on both soil zones based on a map or management zones. So things where things have happened differently. So we can see how this could be useful for what we want to do for carbon, but it's probably not going to be the whole answer. So recommended amendments based on test values. So you're going to send these samples into a testing lab and they're going to give you some sort of recommendation back. It's a little different for carbon and we haven't really gotten there yet. Another way that we can sample that Christine mentioned is just to do stratified random sampling. And actually it's a really good way to make sure you have good spatial coverage, especially if you don't know, you don't trust, or maybe if the soils are fairly consistent across the field and you just want to make sure you caught all of your variability. The issue, of course, is that we're not just taking a surface sample of carbon, right? We have to take bulk density and coarse fragments, as has been mentioned before, excuse me, and we need depth. We need to know what is going on with a different depth. And then eventually we're going to need all that kind of research that went into those fertility trials, right? We're going to need to know what happens with a given practice, not just occasionally or for an individual project, but in lots of places with lots of different kinds of soils. And it makes things, well, I don't want to say they're more complicated, but it takes time to do that work. And I don't think that we've had that same space to do that same kind of joint collaborative research that we really need. So the standard soil carbon calculations, we're going to use that bulk density, that's the, P, SOC concentration, and then you got to take out those coarse fragments. And then you do that for individual layers. That's how we usually send samples to the lab, right? You take a given depth, a given layer, and then you take those and you're going to combine them together and you'll get some sort of total carbon stock. Now, there are several component parts to this that can, complicate issues, right? So soil organic matter is more often measured than soil carbon. And a lot of times we will do a factor. We assume that most of it, 58% or so, is carbon out of organic matter. And we actually looked into this last year thinking, well, that seems so generic and there can't possibly be one for all kinds of organic matter. But honestly, we, as the Soil Survey Center, with all of the samples that we have and all of the ways that we've measured soil carbon in the past, we couldn't come up with anything more reliable than this. Should it be different? Yeah, we probably think it should, but we don't have a better one to replace it. And then carbon, it's often measured as combustion, as Lance and others talked about in the last group. But sometimes you can model it through other means. You can do proximal sensing. You can remove some sources of air and sometimes add others. But carbon is not, as mentioned, the hard part. Bulk density and coarse fragments can be a lot harder. You have to know what you're measuring. You have to collect a sample with known volume, or you have to have some sort of function where you model it. And we've done that in the past, and I'll talk a little bit about that. But the coarse fragments can be harder because you either have to have a weight and correct it. That means you know what the density of the rock is. And usually we'll estimate that through some means. And actually there's a fair amount of rocks in Iowa soils. It's a lot of till, a lot of glacial stuff happened. And the less is nice, but it's not the whole state. So there's a lot of places where these rocks are a problem. And there's a lot of the protocols that were really developed in ideal situations. Like this is what we can do in a perfect scenario. And perfect just doesn't happen that often. So as mentioned before, you can sum up those carbon layers into a depth, but really when we want to do comparisons, that mass equivalent example is going to be much better. And so I'm going to show you how to do that. When measuring change, you have to have a common base, because the issue is that carbon and bulk density, they kind of go in opposite directions. And because a lot of our management really can jumble things, it can make comparisons really hard. And so that's why that mass equivalent can be important. And I will point to a couple examples of how you can do carbon stock sampling, but honestly, I don't love any of them. I don't love any of the ways they've been presented. They either tend to be too specific. For instance, the protocols on the laboratory stuff about drying, or they tend to be too general. Well, go do this, figure out a good place to take the samples. And it's really hard to generalize. I understand why the directions are that way, but at the same time, it's not super helpful. So measuring carbon stocks in soil survey, we've really kind of broken this down into 3 different ways we've done it. Some of these have been done in the past and we're moving forward, and it kind of, well, it's not exactly linear. It's not exactly, temporal. It's just sort of different questions, different projects, but this is how I organize things in my mind to keep track of what we've sampled and why. So the first one I'll talk about was mentioned, the rapid assessment of soil carbon. There's a website, if you Google it, it's actually was about 10 years ago that we did this now. So the area of interest was the entire conterminous United States, CONUS. We did stratified random sampling. And in order to do that, you have to know whatever you're using to stratify, you have to know everywhere. It has to be mutually exclusive and exhaustive. So every point in the whole country has to fit into one of those strata and only one strata. And that actually can be limiting because some of the things we know are important, we only know some places. And you have to really think about how to divide those out and if you can sample. And in this case, we usually couldn't. So I'm not going to go into great detail about how we did this. I will tell you that initially we were supposed to use visible and near infrared spectroscopy to help and assist to get our numbers of samples up. But we had problems with bias that we could not correct. I think it was based on sample handling. That was part of the issue. The moisture algorithms have improved greatly since we did this. And we tried to go back and see if we could improve the scans we had. And it just, we didn't have our data handling set up in a way that made it very feasible. Let's put it that way. So there isn't enough resources. We can't sample all soil, right? That doesn't make any sense. So you have to do this thing where you figure out where you want to go. And in this case, we're using SURGO, we're Soil Survey. We're going to use that as a basis. And then we're also using land cover classes, land use land cover classes, because we know that makes a big difference. So we split things up that way. We have replication. We know we need to get to that mean value, and we can't replicate, we can't even sample every soil. We know we can't replicate every soil possible. So we did some statistical manipulations to try to make that possible and to average things out the best we can. So we use the National Resource Inventory as a framework, and that has, well, it gives us a statistical spread. It gives us some background knowledge about what used to be there. We tried to get something that had been stable in land use for about 5 years, but the details I won't go into other than to say we did our best. So we collected a bunch of other information to go along with those soil carbon samples, but honestly, it was difficult to use because we're looking at the whole country. And that's a difference between looking at a field and looking at a country scale. It's just wildly different in terms of what you can get out of it. So as I mentioned before, soil carbon and bulk density go in different directions. And depending on what land use you're in, you can see a little bit of difference. The only two huge things that show up are forests have a very definitive O-horizon at the very surface with low bulk density and high carbon values, and wetlands, especially organic wetlands, have a lot more carbon with depth and lower bulk densities with depth than the other land uses. And honestly, those were the biggest differences. So within strata, within region differences were so large that the regions don't show up that well. When we look at the overall carbon stocks, I mean, like I said, wetlands have a lot because of that depth with the organic layers, but everything else is pretty similar. You might notice that rangelands are a little lower, but that's actually because most rangelands are in fairly dry, fairly, well, low carbon areas. So in that case, I mean, this might be a map that is, you're pretty used to seeing, where the Southwest has less carbon than the rest of the country. And really all this tells us is an inventory. It's a good baseline to start from. It's a good where do we go from here map, but it's not going to tell us about a lot of detail. In the most detailed version we could come up with, this is using SURGO and the National Land Cover data set to extend those measurements that we've taken to the whole country. I mean, a few things pop up. If you know the Sandhills in north central Nebraska, they're there, but you can't even see the Des Moines lobe on this map, guys. So, you know, how detailed could it be? So anyway, that's really what I think about RACA. Like, what did it give us? It's that one-time general CONUS inventory, but it didn't really tell us anything that we want to know about specific management practices. And it certainly isn't going to tell us about change without a lot more work. So, and I say that because we may end up using it as a baseline when we go forward into these other. So for comparisons, we do something we call dynamic soil properties. And these are projects that are really meant to hone in on a specific kind of soil and some specific management systems. We have some national instructions and bulletins. Soil survey is really good about having standards. We say exactly how we're going to do it. We say exactly what the data means. We know where we put it. And so in that way, we are able to collect a lot of data that can be used by others, but answer specific questions for us. And so an example I wanted to show of that is in the northeast part of Nebraska, where we have a catena of different soils, and we've linked those to similar soils. And then we've measured some of these dynamic properties, including soil carbon. So in this case, it's a little hard to tell from the map, but Moody is at the top of the hill, Nora and then Alcester is at the bottom. And we hope to do it in this catena fashion because, as was mentioned, carbon moves. So we don't want to just look at it in one place. We want to look at it in multiple places and see how things are changing over time. Whoops. And if you look at, I'm not going to go into depth of the kind of data we got back, but in this case, really the only changes we were seeing in carbon is the very, very surface. And so that's interesting from a lot of different management perspectives, but honestly, it doesn't end up making a ton of difference in the carbon stocks. Another thing that we've used with these DSP projects, and I'm throwing an aggregate stability slide in here because that's what I had, but you'll notice that different kinds of soils, not in wildly different locations, but a little different. One is sandier and drier, and one is clayier and a little wetter, have very different potential values and very different aggregate stabilities for these different general management categories. And if we can start to put those same values on carbon, then we think that that gives people who use soil survey something to shoot for, and possibly gives us some way to extend the stuff that we know. So in general, we're using this to assess soil condition. Like, are these management systems different? And then we want to be able to aggregate those observations and link them to the rest of our management and soil information and really calibrate and validate models. We're not going to be able to measure everywhere. So we're going to have to use these values and these really carefully taken samples to link to things that can extend in other areas. So I'm going to touch on this last one super briefly because we haven't really done this yet. You guys, everybody in the last group is talking about really, I mean, you're talking about measurement, reporting, and verification, but really it's about monitoring and how do things change over time. What do we get? What's our bang for our buck with conservation practices or just any management system in general? And in monitoring, we really want to get to that measuring one point over time. In soil survey, we definitely have not led this effort. And a lot of times soil scientists aren't always in the room when these decisions are being made, but we have this history, as I mentioned, of these really good standards. And so we think we can use that. We think we can help others adopt standards within NRCS and elsewhere to measure carbon in like a repeatable, understandable fashion. So we have a lot to offer. It's practical. We've got these, while these are scientists, they're not researchers that do soil survey. Most of these people have, you know, they're trained, they might have graduate degrees, but they're not producing papers. They're out there producing something for land management decisions. And so we think that we can, you know, bring something to bear. We also think that soil survey in general just tells you a lot about what you should be looking at. For instance, I see a lot of things where people do like fence row comparisons of how two things match up. And if you're on a different soil or you don't really think through the history, that may or may not make sense. And we think soil survey can help with that. So we think we can say a lot, but we also think that, you know, there's more work to do. We don't know everything and we recognize that. So I'm going to blow through a couple of these slides because I think they've been dealt with previously, but fixed depth doesn't work when bulk density changes. As has been discussed really briefly, this is going to be difficult for accounting And it is interesting to me that the carbon registry stuff has gone in the direction of fixed depth. I understand why. It's easy and understandable, but at the same time, it's difficult to do the accounting if you don't have the same mass of soil. And in this example, if you go from no-till to tilled and you've just like fluffed up the seed bed through tillage, even if your carbon did not change, then your stock calculation could. And that's really not, it's not defensible. Like I can't defend any carbon changes. And so another example of that from the FAO documentation that I won't get into, but that's being leaned on a lot as a way to do this. So I think we should take the examples they've given us and really use it. So our current approach to carbon monitoring and evaluation, we're going to coordinate with USDA efforts so the data is compatible, pound on data. Context is hard, like we talk about how to measure soil carbon data and how to store it, but in reality, it's the stuff about management and what happened there and making all of our systems and how we record what tillage implementation was used. I mean, that's the part that's difficult. And so USDA so far has taken this hybrid approach where we're doing both external agreements and we're doing some of our own work, but we've got to make our data compatible or we won't be successful at the end of the day. I think I just stepped on my own slide there. Data management will be key. Several entities are creating these data collection apps. We've got to make sure that we can all work together. And so with that, I think I'll wrap it up there and I'm happy to take any questions.
Awesome. That was great, Dr. Wills. Let's see. If folks have questions, we can ask Dr. Wills a couple questions right now before I introduce the panel. So one of the questions I had, coming out of the last session and maybe, the idea of collaboration is coming up here repeatedly. So, can you just kind of tell us about some of the collaborative groups that are out there already in terms of working on these issues, and especially, I know you're involved with several already.
Well, the collaboration issue is interesting because we have to be really careful about PII, personal identifiers, and we don't want, well, I work for the government. We have to be really careful. We can't let anybody's data get away from us, and we can't share something they don't want shared. So that's an impediment. Saying that, we have a collaborative research program, and that's been our main way of bringing others into the conversation. We also have some good working relationships with some, like the Environmental Markets Consortium, that has asked for advice, and we are always happy to give advice. I don't think we're not all the way there. We work with Christine's group a lot. We've worked with, we'll work with pretty much anybody, but the issue of sharing data is very sensitive. And I don't know, the federal government has put a lot of effort into having research grants now say they have to share data, but there are so many entities collecting information on different people that I don't think there's any way that it all lines up. So that's not a very good answer, but we're still working through it. Even within the government, it's hard for us to share data.
Got it. Yep. I certainly get that. Yeah, I'm just wondering if there's a discussion of ways where maybe the specific spatial XY coordinate of where the data aren't collected, but some, summary statistics, right? Or,
right.
Aggregate it by, I wouldn't say county, because I don't think that is that relevant for, these kind of biophysical processes,
right.
But, some other unit, some ecoregion type of unit, right?
The aggregating and how to share is difficult, especially when we're talking about the proximal and remote sensing stuff, which really requires that actual location to be useful. We have done some work on anonymizing stuff, and that, because usually the issue is that in some readings of the rules, like as soon as the XY location, it's PII, right? And that's hard to get away from. So internally, what we've been advocating is to make sure that our data models and our data dictionaries are really tight and we're really defining what everything is. So then even if we have some way to anonymize or aggregate or whatever, it's defined exactly what was done to get there. That's our only hope at this point.
Okay, super complicated stuff. So I'll just encourage folks online, if you got questions, please put them in the chat. I'll try to follow them as much as I can. Otherwise, get some help from other folks here as well on the panel. So with that, I'd like to introduce the rest of our panel of experts. And I know there's a lot of expertise in the audience too. So again, just chime in. So I'm just going to go based on how I see folks listed here on the screen. So Stefan Galens is a research director at Practical Farmers of Iowa. I'm really excited by all the work that he's doing with farmers. I know there's lots of questions among watching the PIFI listserv about these kind of topics. So really excited to have Stefan share some of those questions and how PFI is addressing it in research trials. Let's see, we have Brian Hora from Continuum Ag. Brian is a farmer and also senior advisor with Continuum Ag. So excited to hear your comments. Again, you're putting all this knowledge into cropping system and trying to drive yield as with the information that is being summarized here. And so really excited to get your take on all of these discussions. Peter Caravilla, sorry, Peter. I would practice, Stephen, and I still pronounced your name incorrectly. But Peter, it's great to have you here. So Peter is also a senior research scientist in charge of analytics with Iowa Soybean Association, and again, conducting a lot of work with farmer trials, and we're anxious to hear you talk about that. Ala Kahil is a PhD student in agronomy here at Iowa State. And, one of the things I love about interacting with Ala is that her passion for soils is just, it comes through her, and she makes all those around her really passionate about soils as well. So looking forward to hearing you talk about some of the things that you're thinking about in your research and what you're learning here today. And then Professor Fernando Miguez, congrats to Fernando. He was promoted to full professor by Iowa State this spring. I'm going to keep saying that, Fernando. So it's such a great thing to have your work and accomplishments recognized. And Fernando does a lot of work on the interface of data collection and modeling. So looking forward to hearing your take on this afternoon's discussion, or this morning's discussion. So with that, I'm gonna pass it to the farmer first. Really anxious to hear what Brian has to say about the discussion we're having here today.
Well, hope you can hear me all right. It's been interesting, and as I've listened to all the discussions and very in depth, trying to think back to where is the what's going to make the farmers jump on board and really pay attention to putting carbon into the soil. And there's a lot of work that can be done. We realize that, and a lot of tremendous variability out here in the practices that we all engage in. And I believe it was Dr. Laird earlier talked about the modeling, and a lot of the programs that are out there are based off of what growers are actually going to implement, and utilizing that as a way to get a basic direction as to how much carbon we're going to put back into the soil and clean up the atmosphere. And from the farmer perspective, it goes way beyond that for me to have interest, and for other farmers to have real interest in this process. Carbon's gravy for us, and carbon programs are gravy for us. The real driver of what we have to do is profitability, and that's based off of the production that we have, which all nutrients drive that production. So whatever the system ends up being, we have to look at it as a holistic way of producing crops and livestock in whatever we do. So that approach to me is what's going to have to be key, and to make it economical, because a 10, 20, maybe $50 an acre carbon payment is peanuts compared to the hundreds of dollars per acre we're spending on fertility, and potential thousands of dollars of revenue that we have per acre out here. So all these programs, as we implement in the impacts it has on us financially, we can change things in our production practices. And there's just so much diversity as far as the different types of things that we can do, and giving credit to those that are really making the changes and leading the way. Not just financial, but the understanding of how they can practically change things on their farms and for our environment is something that has to be considered.
Fantastic. Thanks so much for those comments, Brian. Ala, I'm going to go to you next.
Hi, good morning. Thank you, Dr. Sheltimore, for the invitation. It's very actually nice to start Friday morning hearing about all of this wonderful conversation about carbon. And thank you, Dr. Wells, for the engaging talk. I really appreciate that you pointed out the depth factor, or you actually pointed that we need more soil organic carbon stocks measurements with depth. And this is something that I have been really interested in. I did my master's here at Iowa State, and I looked at carbon at deeper depth under tree shelter belts and the adjacent cropping systems. And we found some really interesting results. And we actually learned by just looking at the carbon just below the 30 centimeter or the 12 inches of the topsoil. I know there's always a trade-off between whether we sample the top layer of soil, which is the 6 to 12 inches, and have many more number of samples, or go deeper and have less number of samples. But it's also really interesting to look at the type of variations in bulk density and actually other properties with depth. One of the interesting findings from our study, we found that the subsurface soil, which is 30 centimeter and below, contained actually 51 to 52% of the soil organic carbon, and most of the total carbon in the profile actually was in the subsurface soils of our cropping systems. So this is really interesting to hear that we need to focus more on the depth component to better understand the carbon stocks. As someone who had trained on being in the lab, analyzing more samples, it was really exciting to hear about the new technologies like remote sensing and AI that are being developed to actually measure this carbon. But I also think that this maybe we just need more field work and soil sampling to understand the variation and maybe do some more verification since these properties just change with time and space, and we know that. But yeah, overall, I'm very excited to learn more about these technologies. And I just have one question for the keynote speaker. Since you mentioned the depth component, how deep do you think we should just go and look at the carbon in the profile? And
Awesome.
thank you.
Oh, yeah. Awesome. Thanks a lot. And we'll circle back to that question when we after we hear from the other panelists. So Peter, can you share your thoughts?
Thank you, Lisa, for the invitation to this symposium and this panel. And Sky, thanks for a great presentation. Glad to see you again. We spent a couple of years at the agronomy department, at the soil science, major in soil science. And of course, always in soil fertility, we usually sample to 6, 12 inches. And you have a big track, so you have a lot of hours to sample to the 1, 2, even 3 meters. That was very, very appealing. From my perspective, as working for a farm organization and non-for-profit and private, I want to address emphasize two pieces. One is I didn't use my soil science background for many years, unless maybe 2 or 3 years ago, where a lot of interest in carbon trading and so forth. So I consult a group called Soil Water Outcome Fund. It's a kind of for-profit part of Iowa Soybean Association, where I help them to develop a protocol for monitoring and reporting the carbon parts of this action. And then I also would like to follow up what Brian said, that a lot of time when we talk to farmers, they're really thinking about economics. And one of the important part is to develop a tool and some kind of management tool and ability of farmer to see all of this cost. So for example, Christine mentioned that about cost optimization from a sampling perspective from those who are really trying to optimize sampling, but it's also the cost optimization from farmer perspective and agronomists. And just recently, we have a small project with Iowa and RCS. It's a conservation innovation grant where we develop so-called a cover crop economic simulator. It's online, free for public tool. And again, cover crop, it's a big deal in climate smart and soil health management. So in this tool allows not only to simulate, but consider the cost, but also so-called cost mitigation opportunity. For example, a user can plug different state and federal program, how much they would offset this cost. Then the tool also can estimate the value of cover crop in reducing soil erosion based on the current land prices. And the tool also allows to incorporate the value of soil health, increase organic matter. But what's important is that we had a farmer panel, and in fact, 1 or 2 farmers here at this meeting online, and they suggested us to develop these so-called the added value for the greater good, or the added value for the public good. And those include specifically like impact on climate, impact on water erosion, impact on other things like crop insurance. So all of these costs can be considered, and this ability to simulate this and play can really help farmers to be more interested in this and improve adoptions.
Very good. I'm hoping somebody can put the link to that tool that you mentioned in the chat so we can all check it out, because that sounds like a really helpful tool and something that a lot of people would want to check out and maybe play with. All right, let's move on to Stefan.
Great, thank you. And happy Earth Day, everybody. I think it's safe to say that we all want to be part of the climate change solution, and that sequestering carbon or putting more carbon in the soil is something we all want to happen, or to be true, or to be universal across all fields everywhere. But I'm not so sure that the relevant or recent scientific literature necessarily supports this. Regardless of protocol, there's been lots of talks of that, but there's even a consistent signal telling us that sequestration predictably occurs broadly in all places, at least when considering, like immediate timescales. And Dr. Laird kind of touched on this a bit in the previous panel. Is the carbon we're measuring going to stay sequestered for the long term, or will it just be respired back into the air? And I believe Dr. Wills kind of touched on that a little bit. And I appreciate her underscoring the importance of landscape position and soil type for when we interpret soil test results, because that can definitely influence things. But let's say, for instance, that we do measure some sequestration. But I wonder if about the net emissions from agriculture, and if we're still net C emitters despite a little bit of sequestration. So how reasonable is it for us to expect sequestration or carbon removal from the atmosphere to offset the emissions that are continuous from agriculture, like enteric fermentation from livestock, fuel use, inherent energy and fertilizer inputs? Or what happens when those practices we put in place for a while get reversed for whatever economic reason or other social reason, such as perennial pasture being converted back to annual cropland? And I apologize for all the question marks, those rhetoricals there. But finally, I think it's important to point out that a lot of the practices or management systems, and I think Brian kind of touched on this, that are championed to sequester carbon provide so many other benefits and opportunities for us. And Peter kind of mentioned on this too with the tool that he's developed at Iowa Soybean. Right, so this is preventing soil erosion, improving water quality, improving water infiltration, provisioning of wildlife habitat, providing opportunities for farmers to reduce fuel use, costs, chemical input uses. In particular, I always think about fertilizer inputs that require a lot of energy to produce and emit a lot of greenhouse gases in their production. And so I really appreciate at the top, Dr. Dean Robeson cited the importance of our soils, our organic matter for soil fertility and for our deferred maintenance of that soil organic matter, as he put it. So if we nourish that soil organic matter, or farmers nourish their soil organic matter, we have a sustainable source of soil fertility for consistent plant productivity. So our crops, our forages, our trees, et cetera. And Brian kind of mentioned on that a little bit about that's what really drives some farmer decision making, is the consistent productivity of those things. And that reduced reliance on external inputs for soil fertility, that's what can really lessen our carbon footprint, improve bottom lines. That, to me, the farmers I work with, that seems like a real solution, and that those are very reasonable potential outcomes to exploit, and that benefit farmers in rural communities in the end. So I'll leave it with that.
Yeah, fantastic. Everybody's bringing up really, really great points. Super appreciate it. And just highlighting that, there's so many things interrelated here, and this is complex stuff, which is why we're giving attention to it, right? Forward that conversation. And Fernando.
Thank you, Lisa. As Stefan said, happy Earth Day. Thank you for allowing me to be part of this panel. I would say that I maybe wear at least 3 hats. One is as an agronomist. The first hat I wear as an agronomist. I think the remarks I would make echo a lot of what Stefan was saying and Brian. I'm surprised, I think about going back to the Earth Day and the sustainability that Dan brought in. I think as an agronomist, that sustainability to me means maintaining profitability, maintaining yields. And the practices that I think are ideal as an agronomist do not necessarily increase soil carbon. So soil carbon, I think this is something like Stefan was saying, is soil carbon to me is one piece out of the sustainability puzzle. For example, something that Sky was mentioning, and I wonder about, is many practices as an agronomist that reduce compaction are going to reduce bulk density, which is desirable. But that reduction in bulk density is going to reduce carbon stocks. So we could be making a lot of improvements agronomically and in the soil that in terms of carbon stocks looks like they're not changing, because maybe we're increasing the carbon concentration, but we're reducing the bulks and density. So I'm going to say a word that I don't know how you manage not to say it, Stefan, but the word nitrogen, right? Right? Because you were talking about fertilizers, but yeah, so I think that, a key for, I think in terms of productivity is managing that nitrogen. And I say that because in the carbon report that we wrote, while we would start talking a lot about carbon, we said, but nitrogen is a big piece here. We need to optimize nitrogen management. We need to optimize fertilizer management and reduce nitrous oxide emissions, which I think the advantage is that we do not have, if we can optimize our fertilizer usage, we do not run into the problems of additionality and permanence that are required in carbon markets. So that's something I just had to mention as an agronomist. So I'm going to change my hat now and put the hat of a statistician. And I think a big challenge here, something that goes along with what Sky was mentioning, is to me a big challenge here is that the spatial variability in carbon is huge compared to the temporal changes that we're trying to detect. So carbon changes slowly over time in the soil. and the variability in the landscape is tremendous. So that's something that to me really stands out as the kind of system we're working with, and something we need to keep in mind. A third hat I'm going to wear now is the hat of a modeler. As I was thinking about all the different sources of error, I think about bias and variance, the two big components. You know, bias is related to accuracy that I was mentioning. And I really appreciated both presentations, because I think a lot of these things came out of both presentations. As a modeler, I think about propagating that uncertainty all the way from lab measurements up to the, for example, uncertainty related to what protocols we use or what models we use. In the chat, there was some mention about the reliability or how much we can trust COMET or other models that might be used, and the importance of being able to fully account for all these sources of uncertainty, measurement uncertainty, sampling uncertainty, structural uncertainty, if we want to have credible carbon markets. So those are kind of the three hats I wear and the three remarks I made. So thank you again for all the really great presentations today and great input. And yes, we can go back to questions.
Yeah,
Thank you.
Yeah, wonderful. Thank you, Fernando, and thank you everybody for those comments. We'll start with a last question to Dr. Wills about any kind of recommendation in terms of sampling depth.
Right. So I'm going to answer that question like any good pedologist should. It depends. Like some places, honestly, I'm in our current discussions, which I think this might speak to some previous questions in the chat. In our current discussions about how to make this a SEMA or a supported activity that NRCS supports, I'm recommending that we go to 1 meter, and that's just based on the area that I think that SEMA will be most applied, which is the upper Midwest. So Iowa will be part of that. Now, when we're in areas like coastal zones, where honestly there's more carbon storage happening than in a lot of agricultural systems, we think we need to go to 2 meters, because those systems are just so dynamic and changing so quickly that we think we need to do that. And soil survey in general, we're talking about inventories, we always want to go to 2 meters and maybe beyond. But when you're just looking at change, that upper 30 centimeters is really important. But in order to do the adjustments and to really make sure you've tracked everything happening, then I think it's safer to go to a full meter. Of course, then the issue is how many people can get to a meter, and 3 feet of soil is not insignificant to deal with. But that's my, I think we have to go deeper. We just have to. And actually, the other conversations I might pipe in here, the life cycle stuff, I saw the question on comment, and it's super general. I don't know anything about the grazing systems and carbon. That's not my area. It's all based on DACENT and other models, but then generalized, and it does take into life cycle accounts. And honestly, when it comes to greenhouse gas emissions, nitrogen, fertilizer inputs, tractors, all of that is honestly bigger than what's happening in the soil, and the temporal turnover is much, much faster. So, we're talking about soil carbon. I, of course, love soil carbon, but sometimes we're at least not going to be the fastest change.
Thank you. That was really excellent and clear. Thank you. Fernando, I see you addressed Ross's chat. Can you kind of just summarize that and why you think that's an excellent point?
Oh, I could read it, but I guess I think everyone can read it, but he's pointing out that the expense or the trouble of measuring to deeper depths does not align with the idea of the carbon markets that are just simply trying to track changes of soil carbon over time. One of the things that I could add to that, and perhaps this is more of a question for someone else that might know, but I think the interest in remote sensing, does the remote sensing approaches allow us to go to a depth of 30 centimeters? How deep do we think that we can inform our understanding of changes in soil carbon over time from remote sensing products? This may be a question for some others in the audience.
Great question. Does anybody here have some knowledge on that? How far LiDAR can penetrate or other remote sensing tools? Go ahead, Sky.
I would just say it doesn't penetrate. It builds a model of the surface, but then we can correlate the model of the surface with things that are going on below ground. And Bradley talked a little bit about that. It's all about understanding the landscape. It's not, you're not actually sensing anything.
Lisa, I have a comment related to the model and Fernando's latest statement. In practice, a lot of these carbon programs, they try to match the modeling depths to the actual depths. For example, the Comet farm, right? I think the public version is 0.6 inches. And that's why many of these programs use 0.6 or 0 to 12, 30 centimeters. So that's one of the limitations of modeling, which is very critical part in monitoring and of course reporting and definitely assessing temporal variability.
All right, thank you, Peter. Any other follow-on comments from our panelists on the discussion here or something that anybody else said? All right, if not, we do have some other questions. One from Michael. Are there any correlations between soil biology and soil carbon?
I hope so.
Yeah, I'll take that for just a little bit. That's one of the things that we're monitoring, and I didn't get too far in depth with it, but through Continuum Ag and on our farm here, we are trying to understand that soil biology and the CO2 respiration, so the gaseous form of carbon, and what's in the soil. It's a very difficult thing to do. We do a lot of Haney soil health testing so that we can measure, we can get the value out of the test. First of all, I can measure my nutrients, my micronutrients, but I also am measuring my organic and inorganic forms of several nutrients. So it helps me in the process of reducing my nitrogen, first of all, because I'm taking full credit for all the organic nitrogen that's in the field. And the processes that we're doing using, we start with some Sergo, the maps to lay out our zones and trying to be economical about it. We've gone away from grid sampling. That process of trying to balance out nutrients through variable rate applications on 2.5 acre grids just was not working. So we've gone to zones, again, based off of primarily Sergo information and as well as yield maps and such. But in the process, we are now sampling, I think we're in year 4 of sampling weekly on about, a couple of different farms, numerous locations on farms, same locations every year. And some of this is, again, through the Soybean Association, where we'll go out every week, April through October, and watching what's going on with soil biology, CO2, and how we're tracking that week to week. So again, gathering as much data as we possibly can. Expensive process, obviously. And in those samples, we are just running the 0 to 6 inch sample. That's where most of our soil biology is anyhow, is in the top 6 inches. So we're trying to correlate that to carbon and the carbon that we're putting away. And we are seeing massive changes in the amount of organic matter over about a 10-year period and what we have changed. So as we get further in depth with cover crops and utilize them further and further, we're finding the need for a lot more residue on the surface because the soil biology is gobbling all that up. Obviously, we're emitting more carbon as they degrade and as the process of degradation of the material the organic matter happens. But our crops need that carbon dioxide as well. So putting that right back into the crops as they grow.
Thank you, Brian. Yeah, Sky, it looks like you have a couple of thoughts on the question about when the baseline should be established.
Yeah, I'll find a link and put it in there with a little bit more information on how we're doing, but it's really, it's tough. We tend to report conservation effects based on some long ago moldboard plow baseline, which is really convenient for a lot of reasons, but it doesn't necessarily tell us what a conservation practice is what effect it will have in reality. Because, you know, there are people that are still doing moldboard plows, but not most people. So it's it's a tough one for us, really is. And so that's back to our data thing. Like, we just try to keep track of what is happening to the best extent we can. And then maybe later we'll have a good baseline.
Thank you. Let's see, Fernando, would you like to take the question there from Chowquin Crystal Lu?
Let's see. I don't know that I'm the best. How do we evaluate the actual? I would see if someone else wants to answer that question.
Okay. Anybody else want to talk about
what I can
variability?
say from a statistical point of view is that the more variability you have, and the smaller the change you're trying to detect, the more samples you need. So we were talking about samples before, and the importance. One of the things I would bring up is the trade-off. There's usually trade-offs between bias and variance. And that, I think, was something that wasn't explicitly stated, but something that was very clear from Christine's presentation.
Great. Yep, thank you. Anybody else want to comment on that? Well, I have one more question. I think this might be what we use to wrap it up. But you know, one of the things that came up in the previous panel, David Laird mentioned it, and there was some discussion, was with these carbon markets. You know, the challenge, all of the challenges with verifying changes in soil carbon, and then the time required. You know, David suggesting really what we need to do is move towards a more of a practice-based market. And, you know, that's also something that in last year's Carbon Removal Forum, Phil Robertson also suggested that it needs to be based on practices, and then a regional approach, which was something that was recommended in the recent report on soil carbon measurement in the journal Science by Emily Oldfield and some of her colleagues. And just kind of curious, from this group, what is your reaction to that? I'm not advocating or trying to dissuade from that type of approach, but I'm just curious what this group thinks about moving towards more of a practice-based framework rather than field verification.
I can just add that this is probably good for stratification by practices, and that we can reduce noise. It has merit from our perspective.
Okay, thank you, Peter. Stefan, how about you? What do you think?
Well, I guess I'll read it. Like, what if those practices actually don't in the long term sequester carbon? Are we going to be okay with that? As was mentioned, there's a lot of commercial interests in this, you know, that only work if something happens. What if something isn't happening at all places? Because it might in some areas of the country, but maybe not here, maybe not there. So I'd be careful about that.
Okay, thanks. Sounds like healthy skepticism. Brian, it looks like you wanted to say something there.
Yeah, I'll go back to that again. As I mentioned earlier, Dr. Laird had mentioned that, and that is the one area where we have the easiest area for us to collect a tremendous amount of data, because equipment that is utilized to put crops in, harvest crops, fertilize, run a tractor across the field, whatever it may be, it is very easy to track it. Most modern equipment is fully equipped to do all of that. So we can collect tremendous data over a very broad area. And if you can verify the changes that are going on in the soil with the sampling, which we're going to have to do, we have to verify the change. But the modeling, you can, there's a lot of errors in it at this point. We have a long ways to go. The COMET program was mentioned before. In the COMET programs, if you have cover crop out there, yeah, we're good until we plant. And then it's assumed that we no longer have cover crop. Well, those that are taking cover crop well into the summer before they ever terminate it are putting away a tremendous amount of carbon because of all the growth that we have of plants. So we're going to have to track all that data as well and utilize that to fully build out models of how we can put more carbon into the soil. And the other thing with that as well is carbon. I don't know if carbon is going to be the answer. I have my skepticism as well as to how long it can go and the real value in it. But programs that are building and putting carbon in the soil, which is your basic soil health principles of reducing your tillage, reducing soil disturbance, keep green plants alive and growing out there as long as possible. There are so many other benefits to that in water quality, air quality, and even financially for the growers. And then as well as the quality of the product that we produce. That long-term, there is real value here. And it just has to be taught to people, and it's going to take some time because it is complete conversion from where, as mentioned, Sky mentioned a while ago about the moldboard plowing. Yeah, there's still more moldboard plows around, but we're getting rid of those and learning new production systems with new technologies. And there's a tremendous opportunity for everyone involved in agriculture to really push forward new practices and in a very climate friendly way.
Awesome. Thanks, Brian. You farmer innovators, you give me so much hope for the future. Thanks for all the work you do and sharing your knowledge with everyone. Ala, maybe 1 minute for Ala and 1 minute for Fernando, and then I'll move to Vice President Dorhout.
Yeah, again, I have been enjoying the discussion, learning a lot of fantastic things to consider in the future research about carbon. And I usually think about soil organic carbon in general in two lenses. The first one is just the soil health and the carbon credit we've been talking about, and the other one is just the climate change. So I think there's potential for carbon to help us with these two lenses. So just with more kind of understanding of the complicated issues we are going through, like the sampling, the analyses, the cost. So that's this has been helpful. So I appreciate everyone's pointing out the new information and exciting technology, and I look forward for more. Yeah.
Awesome. Thank you, Ella. And Fernando, any reactions?
So one of the things I was thinking as you were, as we talk about these regional effects and the practices, I think the payment is still made to an individual, right? Even if we look at things at regional scales for the other. What Emily and we're talking about, this technology extrapolation domains, this idea is that we can establish some baselines based on, regional soil combinations. I think still the payment is made to an individual, and an individual is adopting a certain practice. But I think related to what Brian was mentioning, I think the execution of that practice matters, because you can probably do cover crops well, or you can do them not so well, and that can make a big difference in terms of the actual carbon sequestration that is going to occur. We also know that the requirements of permanence means that we need to sequester this carbon for anywhere between 10 and 100 years. So if we're going to be adopting practices and be paid for those practices, we're making a commitment we should be making a long-term commitment. And I think this can be challenging in a social framework where a lot of the land is rented, right? We're not we're not working directly perhaps with landowners. So I think those are things that I think that need to come together in order to be able to pay for practices.
Awesome. Thank you so much, panel, and Dr. Wills, for sharing all your ample knowledge with us and this wonderful back and forth. This is just a great way for us all to learn, I think, about this really important topic. And as so many said, you know, despite carbon markets, we know that soil organic carbon has a lot of value in our agroecosystems and well beyond. So with that, I'd like to introduce our Vice President for Research, Peter Dorhout. Peter has been at Iowa State for about 1.5 years now and comes with very esteemed credentials. He's a fellow of the American Association of AAAS. I'm forgetting all the A's right now. And then also the American Chemical Society, chemist by training. I think he really appreciated some of the comments about the need for interdisciplinarity in cracking some of these questions, and is also a lifetime member of SACNAS, which is the Society for American Chicano, Hispanic, and Native American scientists. And one other fun fact about Peter is he's also an Eagle Scout. So I'll turn it over to you, Vice President Dorhout, to close us out with a few comments.
Thanks very much, Lisa. I appreciate the introduction, and especially inserting in a couple of fun facts every once in a while. As Lisa mentioned, I'm a chemist by training, and really did actually enjoy a lot of the conversation. I've had the pleasure over the past year plus to work with Lisa and Robert and the team at Bioeconomy Institute. We've put together a couple of workshops, and I've had the opportunity to hear from a whole host of experts in this space. And every time I do, I get to learn something new. And but in learning something new, I get to ask questions too. And in particular, I continue to hear a theme, and a number of you raised this. I saw some of this in the chat. This theme of bringing more people together into the conversation, because when you talk about the challenges of being able to measure carbon in the environment, I think Sky may have mentioned this and commented about the limitations on LIDAR and what you're able to actually collect through that process versus being able to actually get your hands into samples. However, the challenges are that you need armies of people to go out there and collect those samples. And so that's an important consideration. And it also really begs the question, what advances do we need in detection technologies? Bringing physicists and engineers and the occasional chemist to the conversation with folks in natural resources and land management and the soil scientists and the agronomists to say, you know, could we come up with an innovative tool that can help address this? And I think there is a need for a National Academies study or a working group to sit down and really have that conversation in the broadest context. I keep coming back to some of the things that folks shared in terms of just, the soil science protocols, and is there a need for reimagining those protocols that are relevant to the big question. Now, what we've learned today, of course, at least what I've learned today, and hopefully others have as well. And Fernando commented on this just really at the end here. We've learned a lot about soil carbon with an eye towards developing credible, and this is the important point here, credible and cost-effective ways of measuring soil carbon on farms and more broadly speaking, soil carbon everywhere. But I ask you to consider to what end. And it gets back to, I think, being able to tell the story to the general public. There are a lot of complex subjects that you've shared today. What is the value of carbon in the soil? What is the value to a farmer to have carbon in her soil? It's not just simply, well, it's about sequestration and taking carbon dioxide out of the atmosphere, but what are the additional value added components to that? And being able to sit down in a local community with an extension office somewhere and extension professionals and scientists sitting together with producers and talking about why this is so important. And really, I think relying on their commitment to quality of life, quality of community, the commitment to the contributions that our nation makes in terms of global food supply, and why having rich soils that support a biome that extends beyond just what we're thinking about growing is so important. Today we've learned about some of the leading methods and technologies, but also this need to continue to invent and to innovate. Certainly in the Q&A that I was following, it comes back to that fundamental science set of questions, and how do we address in the fundamental science the ability to apply what we've learned and make a difference in what we're doing globally. We heard some fantastic conversation and presentations about making better use of the information that we have in terms of modeling and developing in new fields of sensing technologies, but also integrating that field measurement with remote sensing and so on and so forth. And I'm left with the question of, when we think about statistics and modeling, which is a great way to try to extrapolate onto the larger scale impacts that help us tell a story about how we're improving the environment, improving the ability to grow food. What is the role of artificial intelligence in helping us evaluate things and then ultimately predict some trends that we can go out and measure later on and confirm? That's going to be so important as we continue to tell this story. And so, it's forums like this that help us innovate and really bring together experts who can share and learn from one another at different places, whether it's in the field, whether it's in industry, whether it's at the university, and ultimately make improvements in what we're doing. Now today's program was focused on soil carbon measurement. But the overall theme for the forum series and the few that I've been able to join, of course, are carbon reduction and removal. And innovation in these areas are going to be crucial to achieving climate stability and a whole series of other goals. I'm also reminded that when we think about the agricultural industry, that there have been some significant advances over the last 120 years or so that have enabled us to be able to address a growing population that's grown sevenfold since 1900, and to be able to improve crop production by, in that same time period, about 5 times, to be able to feed that population. But right away, you can see there's a challenge in, you've got a 7x increase in population, you've got a 5x increase in food production. A lot of that caused by the Haber-Bosch process that has, in itself is playing an important role in CO2 production and energy consumption, consuming several percent of the world's energy just to produce ammonia to give us that 4 to 5x increase in food production. But 5x is not the same as 7x, and so that means we're going to have to think about either expanding our the land that's used in food production, or continue to improve on the soils that can help us get to a greater X production in food, while not just having those negative impacts on the environment. So those are all big questions. I don't have any answers. I'm so glad that there's so many phenomenal people on this call that are working on developing those answers. But back to this question of carbon removal, carbon sequestration, it's going to take a village. It's going to take a lot of really unique approaches to this, from harvesting it out of the atmosphere to harvesting it out of industrial production facilities. We're going to have to find a way to address that carbon dioxide and methane challenge that we're being confronted with. And there are a lot of really interesting ways of approaching that. And in fact, because I'm sure everyone was paying attention to all of the speakers involved, you missed an important press release this morning, which I'm excited to share with you now. And that is about the work that Robert Brown has been doing in the Bioeconomy Institute for carbon, and this carbon removal team. That team was awarded $1 million X Prize this morning, and that X Prize milestone award is given really as a bet on the future, as a hope that the biochar process as an agricultural carbon sequestration solution is something that's going to have an even greater impact. So I want to congratulate Robert. I didn't see that he was on, Lisa, so I don't know if he's joined us, but if Robert is not here to take a bow himself, I hope that the rest of the carbon removal team is able to take a bow on behalf of that. And Lisa, in your leadership, co-leadership with the of the BEI, you're to be congratulated. This is the start, I hope, of something big in terms of coming up with an arrow in the quiver that we need for carbon sequestration. So I look forward to listening to more of these conversations about carbon going forward. I'm so fortunate to be at Iowa State University with such a talented group of folks who attract other talented folks to address these problems. So thank you all for your participation today. Thank you, Lisa, for the invitation to be able to say a few words. I did have one slide with all kinds of chemistry on it. I think I'm going to resist the temptation and show it. But let's not forget that it's going to take a village of very talented people, faculty, staff, students, scientists from agencies outside Iowa State, as well as right here on our campus to make a difference. So thank you for all you do. Thank you, Lisa, for your leadership, and back to you.
Awesome. Thank you, Vice President Dorhout. And you can send me all that chemistry by email. I totally want to see it. Well, I just get to close us out by saying thank you to everyone, all the speakers, all the panelists, all the guests. Really appreciate this incredibly vibrant exchange on a super important topic. And so this is where we all clap, do your little clap emojis to thank everybody for, or come back online and clap. Thank you so much for, being a part of this conversation. It is going to take a village, and I'm glad that you're in the village and working hard on these challenges and coming up with really incredible solutions to it, all the way from, farmers on the field to chemists in the lab. We need it all, right? Secondly, I want to just again give a shout out to our sponsors. So today's forum was supported by philanthropic gifts from Renewable Energy Group and the Iowa Farm Bureau Federation. It was able to help pay for the cost of staff to arrange, put everything together and bring us here through Zoom. And I have to give a shout out to two key people. So Jim Jordahl, who's a project analyst at BEI. Jim, I said earlier, Jim and Kalina, who works with ISU conference planning and management, the two of them did 99% of the work of bringing this all together. Thank you so much. You make Marshall and I look so good, much better than we deserve, and we really appreciate what you do there. And then I also just want to give a shout out to the fact again that it's Earth Day, and if I can ask of all of you to do just one thing, all right, in recognition of it being Earth Day. We learned so much here today. Let's make sure that even bigger village learns from what we learned here today. So I challenge you all to pick out one thing that you learned today and share it with someone else. Share it with your family member, share it with your friend, a student, somebody in your community, because it is going to take a village to do this hard work and understand what our options are for the future. So yeah, and I encourage you to write that down. Think about it, take a couple minutes here between before you start your noon meeting and think about what that is. Write it down, because we know from science also that if we write something down, we're more likely to act on it. So hearkening back to Dean Robison's initial comments about intention, I'm going to end up with that too. Be intentional about thinking about what you learned today, writing it down and sharing it with others. It's only that way that we're going to grow our community, grow the village, and actually address some of our really big challenges. That again, thank you, Peter, for bringing us back out to the big picture, right, of what we're trying to do here. It's so important to think about those major challenges that we face, and that this science, this application, this innovation is a part of helping us sustain our livelihoods and sustain our communities and sustain our planet. So ask you to think about ending today by, just with really full hearts for all of the things that people here do to make agriculture more productive, make agriculture have a lighter impact on our environment, and make a better future for us all. And I have one final task before we end here today, which some of you are here today because you're also getting CEU credits. So again, thank you, Jim Jordahl, for lining all of this up. And I'm going to share the screen so you have the QR code. And of course, let's see, let me see about sharing my screen. I'm not as elegant at this part as I'd like to be. There we go. Thank you, Kalina. There it is. So you have the code that you need. And if you, if you miss it here, you can always email Jim Jordahl, jjordahl@iowastate.edu, and make sure you get those credits. That's it, folks. It's a wrap. Thank you all. Have a great Earth Day, and pass it on. Pass on the knowledge.
Thank you.